Hey guys, welcome back. We are on 4.3, Soil Composition and Properties. So our learning objectives for today are to understand soils and the different particles that make it up, to understand the connections between particle size and water holding capacity of soils, and explain how to read a soil triangle to determine soil composition. So there are three properties of soil that we're going to focus on, except for we've kind of already focused on the biological component of soil. Now we're going to more dive into physical and chemical properties. So the physical properties are going to include texture and permeability, and I'm going to expand on that. And the chemical properties are going to be their ability to hold nutrients or their nutrient holding capacity. And we've already talked about this a little bit, but it's really going to be its ability to hold things like phosphate ions, magnesium ions, iron ions, etc. So first, let's talk about physical properties, and we're going to focus on texture. So texture of soil has to do with, the texture of the soil has to do with what it's predominantly made up of. And there are three main groups: sand, silt, and clay. You've probably experienced all of these different soil textures. What you'll notice most about these is their relative sizes. So clay is, of course, the smallest size. Silt is sort of in between, and sand is massive. Now, this makes sense if you've ever been to the beach. You can physically see an individual grain of sand very easily if you put it in the palm of your hand. It's very hard to isolate an individual particle of clay. Very, very, very tiny. Most soils are a combination of all three of these things, and there is an ideal combination, an ideal percentage of each of these to make up soil. And I'm going to talk about what that is here in a minute. But we do have a way to be able to determine what these percentages are. Now, what does it mean if something's clay, silt, or sand? Why do we care about that? Really, we care about it because all of those things play into soil permeability. This is basically its ability to hold water, or as the AP will refer to it as, is its water holding capacity. So I like this image because I think it does like a pretty good job of explaining this. But sand, for instance, because of that particle size, the individual particle size, which is massive by comparison, there's a lot of space in between individual sand particles. So it takes a much longer amount of time, or a much quicker amount of time, for water to filter through. It doesn't have a very high water holding capacity. Water just wants to pass through all that space that exists between those giant particles. Whereas clay, which has like the smallest particulate size, it takes a really long time. Those tiny individual particles of clay are really tightly packed together, so there's not a lot of space or room for water to want to pass through. So you end up with a really high water holding capacity. And then silt is sort of somewhere in between all of that. So this is important. Water holding capacity is important because we care a lot about retaining water versus draining water. We want our soils to retain water because we know that living things absorb water through their root systems, and water is required for them to be able to survive. However, we also don't want soils to retain too much water because then it's too soggy. You can get things like root rot or too much saturation, where the plant basically explodes because it's absorbed too much water. And so we don't want that either. So we need a soil that's a mix of sand, silt, and clay, so that we have this sort of perfectly balanced water drainage to water retention. So that basically we have enough water for plants to absorb, but not too much to the point where the soil is overly saturated with water. So how do we determine the percentages of each of those and what the perfect soil is? So luckily, somebody's already done that for you. The perfect soil is something called loam soil. So loam soil is about 40% sand, 40% silt, and 20% clay. This is sort of the perfect combination of accepting water drainage, but also water retention. They also say that anything over 20% clay is going to retain way too much water, and anything over 40% sand is going to drain too much water. So this is sort of the perfect combination. Now, this triangle that you're looking at is called a soil triangle, and this is the triangle that we use to determine the type of soil we have. So you can see on here we've got clay, sandy, loam, loam, sandy, loam. These are all just different combinations of sand, silt, and clay. Now, do you have to memorize all of these different types of soil? No, definitely not. But what you do need to do is understand how to use the soil triangle. So a really common AP question would be something like this. What's the soil type for a soil that contains 25% clay, or 25% sand, 30% clay, and 45% silt? And so I'm going to show you how to do that right now. So I'm actually going to grab a pen here, and we'll do it in, we'll do it in blue, I guess. So the first one that we want to look at is 25% sand. So this kind of got cut off, but this bottom portion of the triangle is sand, and we're at 25%. So the 25% category, here's 20, here's 30. So I know that my sand is going to be somewhere in this range. So I'm just going to put a dot here for now. Clay, I've got 30%. So clay, here's my 30% line. And if you notice, clay has the ability to go two directions. So the 30 line can go this way, or the 30 line can go this way. Now, we'll just leave it at that for now. The silt is at 45%. So at 45%, we're somewhere right here. So silt has the ability to go, sorry, my line is really bad. It has the ability to go this way, or it has the ability to go this direction. Okay, and then let's go back to that sand. Sand was at 25%, so it's somewhere in here. Sand can either go this direction, if I follow my line, or it can go this direction if I follow my line. And what you're looking for is the point in which all the lines match up. And for us, that looks like it's about right here. So in this particular example, it looks like we're either right on the border of clay, loam, and loam, or we're kind of more clay loam. I guess clay loam versus just loam, especially because our clay portion looks like it's slightly above the 20% line, sitting at 30%. So I would call this a clay loam, but it is kind of right on the border, so that might be a tough one. But you're looking for the one that lines up perfectly. Okay, so of course we had all these options for lines coming off the 30, but remember everything has to equal 100%. So 25, 30, 45, it all adds up. The other thing they may ask you to do is go the opposite direction. So they may give you a point on the line. They may say, and actually let me change my pen color here. They may ask you to go opposite way. So I'll do green now. They may give you a point, like say right here, and they might ask you for the percentages of silt, sand, and clay. And so you'll notice that for every point, there's two ways it can go off of. So let's say we're trying to determine the percentage of clay. So for clay, I can either be at the 60% or I can be at the 40%. You always want to go with the lower number because remember, you're trying to add up to 100%. So I'm going to say we're going with the lower number here, the lower of the two numbers. Now I'm going to determine my percentage of silt. So for silt, I can either be at the 20 line or I can be at the 60 line. And I'm going to imagine we're probably going to be at the 20. And then for my sand line, I'm either going to be at the 80 or I'm going to be at the 40. And I'm going to go with the lower number here is 40. 40 and 40 is 80 plus 20 is 100. So I have 40% clay, 40% sand, and 20% silt. Those are the two ways they may ask you to use the soil triangle, and you need to be able to do that. Okay, the next thing that we're going to look at is chemical properties of soil. So soil has ions in it, more specifically things like phosphate ions, calcium ions, magnesium ions, things like that. And we have said that for the most part, those come from the parent rock material. Most of those ions end up being stored in the clay portion of your soil, your composition of the soil. And so when we reference the cation exchange capacity of something, we're referencing how many ions your particular soil is able to absorb and then release to plants that are living in that ecosystem. So it's the ability of a particular soil to absorb and release cations. And this is going to be dependent on the amount of clay that is represented in your soil profile. Usually when we have that perfect concentration of clay, that 20% clay, that's going to be the most ideal for us because it gives us a high cation exchange capacity, but it's not too high to the point where we have issues with drainage in our agricultural setting. So common ones that we're seeing: calcium, magnesium, potassium, and these are all macronutrients that are required for plant growth. So we care about these a whole lot. We want a really nutrient-rich soil, a really nutrient-rich inorganic portion of our soil, but we also want a good we don't want too much water retention. So that's what cation exchange capacity is. And then the last thing, and you guys are kind of already familiar with this, is the biological properties of soil. And those are going to be things sort of like detritivores, right? Earthworms, snails, slugs. Those are going to be responsible for creating that really nutrient-rich humus layer, so that they're contributing to the decomposition. You may also have microorganisms living in your soil. Some bacteria, fungi, protozoa, and remember, bacteria are really important in soil because some are nitrogen-fixing bacteria, and they allow those nitrates to become usable by plants, which are also a required macronutrient for plant growth. Okay, I think that's it for today. Let me know if you have questions, and I'll see you in class. Thanks.